Let's look at adding and subtracting radicals. Let's get started. Okay, first one, we have the 1/3 times the square root of 27. Well, 27 is not a perfect square, but if we rewrote 27 as a product of 9 times 3, then that would be great, because when you have a square root of a multiplication problem, you can take the square root of each of those factors separately. The square root of 9 is a perfect square. That simplifies to 3. So then we have 1/3 times 3, 3/3, give our number a denominator of 1, right? 3/3, that's just 1, times the square root of 3. So that first one works out really well. Now let's look at this next one. 2/5 times the square root of 75. Well, if you think of 75 like 25 times 3, then we use that same idea. Take the square root of 25 times the square root of 3. Square root of 25, that simplifies to 5. The square root of 3 is as simplified as it goes. It's just some decimal. All right, and then we have 2/5 times 5, so we've got 10/5. That simplifies down to 2 times the square root of 3. So looking good so far. Now let's look. We have 5/6 times the square root of 108. Well, 108 doesn't, there's nothing that jumps out at me, but notice you've got square root of 3, square root of 3. All of these have square roots of 3, so I'm just going to see what happens. Let's see what happens if we divide 108 by 3. We would get, goes in 3 times there, 18 there would be 36. So I could rewrite 108 as 36 times 3. And again, the reason I thought of that 3 is because each of these are products of 3. Okay, so then we would have 5/6 times the square root of 36, that's just 6. And then the square root of 3, that doesn't simplify anymore. So we'd have 5/6 times 6, that would be 36. That just simplifies down to 5 times the square root of 3. And then we just combine like terms here. We've got one of these square roots of 3 minus 2 of them. That gives us -1 square roots of 3, and then minus 5 more. We're down at -6 square roots of 3. And that is done. Let's see what happens when we put in some variables. All right, so, and also notice we've got a cube root here. So I'm needing to think of perfect cubes. Let's see, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. So keep in mind those perfect cubes. So I have -7 times the cube root of 54. Well, since 27 is a perfect cube, I'm going to rewrite 54 as 27 times 2. And then I've got x to the 4th, y to the 4th. And let's keep going here. This would be 4xy times the cube root of 16. Now 16 is the square root, is a perfect square, but since we're in the world of cube roots, I need to rewrite that as 8 times 2, because I'm looking for perfect cubes now. And now that's still times x times y. And then I have minus 2x times the cube root of 128. Well, I'm noticing all of these products have, it's a product of 2 times something. So let's see what happens when we take 128 and divide that by 2. We would get 64. And 4 times 4 times 4 is 64. So 4 cubed is 64. So that is a perfect cube. There it is right there. So I'm going to rewrite 128 as 64 times 2 times x, y to the 4th. Okay, so I know I could take the cube root of each of these things separately. Sometimes I like to just circle the thing that's a perfect cube root. So I'd have -7 times the cube root of 27 is 3. Okay, good deal. So now I just have that 2 left over, and I've still got my x to the 4th, y to the 4th. Okay, here's what I'm going to do with my exponents. Since I have a cube root, I want an exponent that is like a 3 or a 6 or a 9, something that divides by 3. Okay, but that's not what I started with. I started with x to the 4th. So I need to keep the track of the fact that I still have 4 x's multiplied together. But I'm just going to rewrite that as x cubed times x, because x cubed is a perfectly cube rootable exponent. We can do the same thing with y. Okay, and those are perfectly cube rootable. Okay, so the number is -7 times 3, that would be -21. All right, and then I'm going to take the cube root of x cubed, I'd get x. The cube root of y cubed, I get y. And then I still have the cube root of, let's see what I have left over, a 2, an x, and a y. So I need to keep track of all that. 2x, y. Okay, and just as a little thought over here, the cube root of x cubed. Okay, so the power is in the numerator, the root is in the denominator. So that's just 3/3 is just 1. So the cube root of x cubed is just x to the 1, which is the same as just plain x. Okay, so there's our first one. Now let's look at this next one. I had minus 4xy. Okay, so minus 4xy. I'm going to go ahead and take the cube root of 2, and that's going to give me a 2. Okay, and then I have the cube root of x of 2xy. So then that would simplify. I'll multiply my numbers there, and so I'd get -8xy times the cube root of 2xy. All right, last but not least, let's check this one out. We have minus 2x. Okay, now I can take the cube root of 64. That's a 4. All right, so now that would be times 2x. Now y to the 4th, I'm going to just rewrite that as y cubed times y to the 1, and y cubed is perfectly cube rootable. So then we would get 2 times 4 is 8x, and then the cube root of y cubed is y. So then that would be times the cube root of 2xy. And now we get to combine like terms. -21 of these things minus 8 more would be -29. Minus 8 more is -37xy times the cube root of 2xy. There we go. Okay, so briefly what we were doing is rewriting the numbers as perfect cubes, and the exponents where the exponent is divisible by that type of root. And then simplifying and then adding like terms. Okay, try this one on your own. Go ahead and pause the video and see if you can come up with the correct answer, which is 2z times the square root of 6z. All right, so pause the video and see how you do. All right, so I'll go ahead and show this. We'd have the square root of 4 times 6, z squared times z, plus 1/4 z times the square root of 16 times 6, and then we still have a z there. Okay, and then we think of what's perfectly square rootable. Go ahead and take the square root of everything. Figure out what's left. All right, so we'll take the square root of 16 and get 4. And then we would have the square root of 6z. Okay, and all those are being multiplied. I can commute that 4 out to the front. 4 times 1/4 would just be 1. Okay, and then a half times 2, that's just 1. So I have basically like 1z square root of 6z plus another 1z square root of 6z. So you're just adding like terms here. We're just going to add those two things up. So I'd get 2z times the square root of 6z. And there's our answer. Done and done. So let's look what happens if you've got a square root of another type of root. So the key here is going to be write these in exponent form. So 1/2, or square root is the same as taking something to the 1/2 power. So it would be the cube root of x to the 12th, y to the 7th. We're taking the square root of that, which is the same as 1/2. Okay, and now this cube root, that's the same as taking something, let's say 1/2 to the 1/3 power. So we have x to the 12th, y to the 7th to the 1/3, there's my cube root, and all of that to the 1/2, there's the square root. Okay, and now I get to multiply exponents. So I would have, let's see, my inner stuff, I'll deal with that in a minute, y to the 7th. Okay, so I have 1/3 times 1/2, that'd be 1 to the 6th. And so this is x to the 12th, y to the 7th, all of that to the 1/6 power. And now I'm going to rewrite with radicals. So the 1/6 power is the same as the 6th root. So it's the 6th root of x to the 12th. And since it is a 6th root, instead of y to the 7th, I'm going to write it as y to the 6th times y to the 1. And then I look at what's perfectly 6th rootable, which is the x to the 12th, y to the 6th. So I would get x to the, it's going to be to the 2nd, because the power is the numerator, the root's the denominator. So that would be x squared, and then it'll just be y, because the power is the numerator, the root's the denominator, just be y to the 1. And then we still have that 6th root of y. And that is done. So often it's helpful to kind of know when to go back and forth between radicals and exponents. Okay, my last one here, I'm going to look at the difference between these. The only thing that's different is just the operation. So in the first one, I have the square root of z times cube root of z squared, and the other one is square root of z plus cube root of z squared. So I see some complicated things going on. I've got different roots, so I'm going to write this with exponents. Let's see, the power is the numerator, the root's the denominator, and now here I get to add exponents. So I get z to the 1/2 plus 2/3, and now I need to get a common denominator. And let's let it be 6. So I'm going to let it be 6, but I'm going to multiply the numerator and denominator by 2. In that second one, the numerator and denominator by 3. In the first one, so I would have 3/6 plus 4/6, and then we just add numerators. So it would be z to the 7/6. And now if we're being asked to write that in radical form, then it would be the 6th root of z to the 7th. Numerator is power, denominator is root, and then this can simplify a little bit. 6th root of z to the 6th times z to the 1, and so then that would just simplify down to z times 6th root of z. So it depends what our instructions are. This would be in radical form. But sometimes you're just being asked to leave it with positive rational exponents, and that would be positive rational exponents. Okay, in this very last one, there actually is nothing I can do here because of addition. I only get to add like terms, and that means that the type of root needs to be the same, and what's inside the root, the radicand, needs to be the same. The only thing that could be different would be if we had something like this, where I think of that like the coefficient. It's how many of them we have. We have 2 of them plus 3 more. We could combine like terms. But that's not what's going on here. Here I have a square root, and I'm trying to add a cube root. There's nothing we can do. This is as simplified as it goes. We're done.